Okay, good morning, welcome back. We are continuing with our free response. So, I believe we're on 2003 now.
Mm-hmm.
So just like last time, I'm going to do the first part, and then you're going to finish off the rest of your homework.
Mm-hmm.
Objectives, we'll be working with work, energy, and power today, and using those relationships to solve problems. So we're going to be calculating net work, not on an object. So I'm going to quickly overview energy and power. We measure energy in joules, which is newtons times meters. You can either store energy or do work, but they're the same unit. Um, Energy is the scalar dot product of force and displacement, which just means we have to be acting parallel. So you're going to use f cosine theta before you multiply by how much you've displaced your object. If we're talking about a variable force, then this will become the scalar dot product of force in the infinitesimal of displacement, which would look like this. So work is the integral of force dot dx. That dot tells us we need to use f cosine theta from A to B. Any questions on energy?
Nope.
Okay, then power is the rate at which we use it, measured in joules per second or watts. So I could say power is the derivative of watts in terms of time. Watts is force dot dx. So this would be force dot v. Okay, so we looked at this a while ago,
Oh.
but we can convert forms of energy from one form to another. So for instance, if I wanted to convert thermal energy into radiant energy, we can do that with a fire.
Mm-hmm.
How can I convert light, radiant energy, to chemicals? Is there any example you can give me?
Light to chemical energy.
Mm-hmm.
Hmm. Radiochemical.
It's a good guess. Can you think of any natural process that occurs that converts light to some form of stored energy, chemical?
Oh, photosynthesis.
Photosynthesis is perfect. Okay, then how about chemical to electrical?
Chemical to electrical. Power? No. Electric power. No. Hmm. I don't know.
If we're talking about a battery, would this be using a battery or charging a battery?
Charging. No, using battery.
Okay, this is using the battery. The battery has stored chemical energy, and we convert that to electrical energy that you can use to run your devices.
Mm-hmm.
Okay, then electrical to mechanical.
Electrical to mechanical.
Mm-hmm.
Hmm. Electric engine. Like electrical car.
Okay. Um,
They convert electricity to moving forward.
Form of machine or mechanical movement. I think you're thinking of a motor, but So for an electrical motor, you're going to take electrical energy and then move that into motion. Versus an engine that takes heat and then converts that to mechanical. Okay, so I could use a motor to convert from electrical to mechanical. Friction would convert mechanical energy to thermal energy, and that completes one loop. Okay, if I wanted to work the other way, an engine could take thermal energy to mechanical energy. So it's like a steam engine. If you think of like a train, and I could take mechanical energy and convert it to electrical energy using an electric generator. Something like a windmill or something like that. If I have a battery charger, if you charge a battery, it'll convert electrical energy back to chemical energy, so you can store it for later. We can use chemiluminescence. So when chemicals burn, they give off light. If you burn oxygen, it burns blue. So that's that blue that you're seeing is chemiluminescence. It's giving off that blue light. If you were to burn carbon, it burns yellow instead. Okay, then radiant energy converts to thermal energy. So it would be a solar heater. So you're using all of the light in order to make something hotter. Okay, any questions on this one?
Nope.
Okay. So we've got a 100 kilogram box that we're pulling along the x-axis. It is sliding along a rough surface, and the position varies with time according to this function. So x is 0.5 t cubed plus 2t. X is in meters, t is in seconds. I want you to find the speed of the box at the time t equals 0 first. What do I have to do?
We derive.
Okay, so if x is 0.5 t cubed plus 2t, what is v?
1.5 t squared plus 2.
Okay, then I wanted to find the speed at t equals 0.
So t should be, no, we plug in 0, so it's 2.
Okay, now this is just speed, not velocity, so we don't need a direction, but I do need units.
Meter per second.
Meters per second. Okay. Part B.
Kinetic energy of the box.
Yep.
So that's 1/2 mv squared. Then if we derive it in terms of t, that's gonna be 1.5 t squared plus 2, and then we multiply by mass, divide by 50. No, divide by 2 is 50. So 50 times 1 point, yeah. Oh yeah, it should be squared. And then we simplify it. So it's 50 times 1.5, 1.5 is 1.25, is it? Can we just write like this?
Okay, 2.25 if you want. Okay. I think you could just keep it like this. I don't think you need to simplify, but...
Yay.
What's your units?
Joule.
Joules. Okay. And then the net force acting on the box?
So net force is acceleration times mass. So 1.5 t squared, if we derive it one more time, then that's gonna be 3t. So 100 times 3t. So that's 300t.
Units?
Newton. And then 3 power. Power is work over time, right?
Yes.
Yes, so
So,
work is integrate of kinetic energy.
um, so work and energy are actually the same unit.
Oh, so is it kinetic energy over time?
Right. So your derivative of K should give you P.
Mm-hmm. So we derive A. No, I mean BA. B first question.
Okay. Um, so dk over dt equals P. And that's the derivative of work in terms of time.
Mm-hmm.
And if I derive this, what will happen?
That's 100 times 1.5 t squared plus 2 times 3t.
Okay. Or 300t times 1.5 t squared plus 2
What?
watts. Okay.
Yay.
Then okay, we didn't have any angle, so we don't need a cosine or anything. Okay, cool.
Yes.
C. Calculate the network on the box done from 0 to 2.
So that's integration from 0 to work is um change in energy. Then we have energy equation in A, right? No, I mean BA. So we integrate first one in here.
Um,
No, I mean BA. BI.
okay,
Is it?
work is the integral of force dot dx
Mm-hmm.
from A to B.
Oh,
What's our force?
that's B. No, I mean B second one. 300 T.
Times dx is t cubed over 2
Mm-hmm.
plus 2t.
Wait, we should derive
Yeah, we need to derive
X,
that.
right?
Okay,
Yeah.
my bad. So this is
1.5 T squared plus 2. Dx. And then we put it in calculator.
okay. I'm gonna write it out, I think. So 300 by 1.5 is 450
Mm-hmm.
plus this is 600. What's gonna happen when I integrate?
That's
T-
150 T cube.
Okay, T, dt. Okay, there we go. So our work is
150 T cube plus 300 T square.
I feel like I'm missing it. Okay, T times T squared is T cubed. Sorry, okay, let's try again. So 450 T cubed, if I integrate, what's gonna happen?
450 T fourth over 4 plus 300 T square.
Okay, and we're integrating from 0 to 2. So upper bound minus lower bound, my lower bound is just zeros, so that'll cancel. So my work is, if I plug in 2 here, so I've got 450 times 2 squared over 2 squared will cancel,
Mm-hmm.
plus 300 2 squared is 4, that's 2 squared that I just pulled out, times 450 plus 300. What's 450 plus 300?
750 times 4 is 3000, I think.
Okay, perfect. What are my units?
Joules.
Cool. And that should be it for that one. Oops. Okay, part D. Oh.
Indicate whether the work done on the box by student. Work done. It should be the same. Is it?
Is there anything that we didn't account for?
No. Friction.
Friction. So with
Yeah.
friction, will the work we need be greater than, less than, or equal to what we said originally?
It should be less than, because friction help to keep stay, and then box 1 to 2. So it's like box energy, box work plus friction work equal to student work.
So you're saying it's going to be,
Less.
you're saying the work needed to pull a box with friction is less than the work needed to pull a box without friction?
Because it's work done by student on the box. No, work done on the box by the student. Oh, wait, by the student. So student is forcing the friction, no, forcing the work to the box, right?
The student is pulling the box.
Oh, then it should be greater if there is friction.
Okay.
If student is doing it, yeah, it should be greater.
Okay, so this is greater. Okay, and you gave me the reason why, but why?
Because friction plus box. How do we say friction work? Friction work?
Okay, the student must work against friction.
Yeah, because box work frictional work against to the student.
Okay, the student must work against friction to move the box on... to move the box.
Mm-hmm.
Okay. Any questions on anything we did today?
Nope.
Cool.
So, uh-huh.
So homework is going to be the other two problems from this year.
Mm-hmm.
And then I'll see you tomorrow for calculus PC. Any questions on anything else? You sounded like you were about to say something. I cut you off.
So tomorrow, no, I heard next week will be different.
So for next week, they're starting to put us on a schedule.
Mm-hmm.